Thanks a lot for inviting me to this talk. So my name is Emilio Calvanese Strinati. I work at CEA-Leti as a Fusion Wire System Scientific Innovation Director. And also, formerly I was a RESIG project coordinator in the 2023, and I still have some small activities until March. And also the 6G goals and CG DISAC project coordinator. I've been accepting phase 2 of the list call. So the topic is 6G goals, which is central semantic oriented communications. And I will actually explain you our CG cool approach to the problem. So if you look for what we've been doing so far, we have been actually constructing generation of communication systems that actually have been working pretty well so far in the content-blind communication approach. It means actually that data has been transmitted without any a priori understanding of how informative was, in terms indeed of the semantic, or how was useful for the receiver to achieve an end goal, so the pragmatic aspect. And actually, the Shannon approach that also people refer to the technical problem, at the end was focused on how accurately can the symbols be communicated and transmitted. And if you see here, it's very schematic way what actually we are all familiar with. The technical problem, we have a source, here we have a kind of source channel encoder, that actually we have some information we want to send to the network. We have some traffic, there's some traffic engineering that includes all the functions we know about the modulation, the waveforms, or the traffic shaping and so on. Now we have a physical channel where we have the approach to noise, interference, and then the receiver roughly we do the inverse functions in order to reconstruct in a more precise way that the information will be sent by the transmitter. And we deliver this to the destination. So there's been the approach. And actually, what also we have been doing since the 3G, I would say, is following the mantra from Shannon and looking for increasing the capacity of the system. And of course, here I'm showing you an expression which is not precise. In all the cases, that's very specific case where you have a single user in a Gaussian channel, which is call length, but the overall mechanics is there, where actually the capacity is achieved by with a contribution of the radio channel bandwidth, so the amount of spectrum used for the communication, the number of uncorrelated pulses, and something which is proportional to the noise plus interference ratio. So roughly the quality of the link you're using for the communication. And actually, if we see what we should do to achieve the factor 1000 target in terms of capacity improvement in 6G, actually, we can see really what has been done in 5G. And what we did actually, we work in a factor of 10 with spectrum. So improve the way we manage the existing spectrum and introduce new spectrum and do also carrier aggregation. Then actually a factor of 10 in terms of using a given number of uncorrelated signal paths through massive MIMO network densification using small cells. And another factor 10, the missing factor 10 actually, by improving the spectral efficiency of the communication through beamforming, designing very high dBi antenna gains with new modulation, with new coding schemes, with new waveforms, and so on. But actually, our question in the project is why we should target such factor 1000 or anyway improving that much the capacity, why we should provide a sustainable and be sustainable with this kind of technology. So the approach is completely different to what we have in 6G goals. And actually the fundamental question is, what if we could say less but understand more? Considering that we are having a network now, which is interconnecting artificial intelligence agents. So reason machines, they're able to somehow understand, infer, and complete the information received. The idea of having semantic and goal-oriented communication itself is not new. It has been already proposed in 1939 by Shannon and Weather, who actually stated that the broad problem of communication can be separated in 3 layers. Level A, which one we already spoke before, the technical problem, which deals with how accurately can the symbol of the communication be transmitted. The level B, the semantic level, where actually how precisely do the transmitted symbol convey the desired meaning to the receiver. And the level C, the effectiveness level, how effective does the receiver meaning can affect it to decide way the action has to be accomplished. So at that time, 70 plus years ago, we needed to focus on level A for many reasons. The mathematics available were statistics, the artificial intelligence was not a reality, computing complexity was not a reality. In any case, level A was not established. Now with 5G, we've been very good in establishing level A. Now the question is, can we look at level B and level C in 6G? So I will not go into details, but what you translate here, that there's this blue part is the one you already know. But actually, if you go to the semantic and effective level, you need to have other components. Roughly at a semantic level or work in the project, you actually to work on what we call semantic message generator. That means from the data, you extract semantics, concept, the relation between concept and meaning, which can represent the essence of the data. And at the receiver, you need to interpret the semantics. And that actually, if the semantic approach of the transmitter receiver are not the same, if the logic and the ontology language are not the same, then actually we have what we call a semantic channel, because we can introduce error not only because of the physical area, we have some kind of noise interference, but because we do not understand each other. If I tell you a weekend, for some of you it will mean Saturday and Sunday, but from other of you, depending on the culture, would be Friday and Saturday. So there is a very potential big problem and having a mismatch between logics. And then at the upper layer, we have this the search station that interacts with the environment. So what the strategical target actually, which are the key concept of the project, is to conceive and test and make operational a system where we understand first and then we transmit. So we go beyond the approach of just blind transmitted bits, and actually what we do in this project to lay out the theoretical algorithmic operational foundation of a novel communication and networking paradigm. Because actually the problem we have that either if us to judge PT what a semantic communication is, answers that we don't have a consensus yet. And the projects aim to lead an answer to how we can define this semantic communication and goal-oriented communication system. So what we focus on is actually on communication where we have communicated only what cannot be deduced or predicted by an AI. So we really want to go to the essence of the communication, but we also want to facilitate the sharing of the knowledge, the consensus building and integration of diverse perspectives, contributed among AI agents that are somehow cooperating to a goal. And indeed also similar reasoning to increase the skills of these AI agents. So while we do that, because there's a huge issue today face about sustainability, scalability, and interoperability. And if you see how 5G, 6G, and also how the world of AI and machine learning have been designed and operate so far are as separate silos. So this actually has been creating critical resource wastage and also creating a lot of exchange of data, a large volume of data, which can be completely avoidable. And this actually has caused cost and complexity rather than gaining accuracy. So in order to reduce this complexity, also focusing on the reduction of complexity on the physical layer, thinks about how many reconfigurations of the network you need to do in order to achieve robustness today, which can be provided by the semantic level. So the why is also because we want to distill or reduce this amount of data. So not necessarily having a system that deliver a factor 1,000 more capacity, but having much more compression capability, much more selectivity in the data. It needs to be shared, censored first, shared, processed, and stored. We embrace two major paradigm shifts in the story. The first one is this goal-oriented approach. We're actually moved from the job approach we have with the ultra spectral efficiency and the oriented communications. We want to send more and more data with the less possible spectrum. And actually, how we do that, we do not just only add more antennas or densify more the network, but we need also to orchestrate all these things. We have to go through all the complexity of massive MIMO, self-free communication, beamforming. You have to consider new relation and content scheme, and so on. But we go for the other approach, was actually go for the effectiveness given a goal of the transmission strategy. That means that some accuracy is not needed in the communication. Some data is not needed at all. So we need to identify the relevant needed information to recover the meaning intended by the transmitter or to attain a specific goal. And then there's the second paradigm shift, what we call the semantic communication, where we move from moving raw data to feed the machine learning AI communication is all we want to do, we actually have this very funny paradox where AI need the data to be trained, to be tested, but also data need the AI to manage all this amount of data. And at the end, also, there's a one approach that actually is complete change now with the semantic communication that as today is the transmitter defining what to send. With the semantic approach, which also we call a pragmatic approach, we are concerned about how understandable and how useful is for the receiver. So at the end, the transmission is shaped for the receiver. So we go for this approach of understanding first and then effectively conveying the intended meaning. So moving beyond exchange raw data, ensure on the knowledge that cannot be reliably deduced and inferred by a receiver. That can be an AI agent, that can be also a generative AI agent. So to do that, how we can do that? First of all, we need to work on the architecture. And actually, what we are already start doing that, we kick off in January this year. And actually, this architecture, we need to have an AI native SIG system architecture which tailors semantic goal-oriented communication. That means that we need to introduce the semantic models, we need to introduce this semantic plane, and also we need to expose the system with these semantic network functions. And we also need to ensure the potential coexistence between, let's say, legacy systems we can call data-oriented systems with the new semantic users. And then how we do that, how do we extract, represent, and use semantics? Actually, we have four major principles. We use causal representation of the data. We use generative AI, where we also take care of how we represent, which are the logics and the language for which we represent the data. And we also use reasoning for semantic communication and pragmatic communication approach, where actually we shape what we send to the sender according to what is understandable, useful, and actually possible to be processed at the receiver. So to close the loop, after doing this theoretical foundation of the work, we also target two major proof of concept. The first one is an in-lab demo for semantic-oriented communication, where we have a transmitter and a receiver. And so it's a point-to-point scenario where actually the transmitter is actually a mobile edge host where there's all the models of the trained machine learning algorithms, and then the receiver is able to, on the request, download such models in order to carry out a specific inference task locally with the desired latency and an energy budget. And actually, this talk started to bring the technology up to a TRL level of 4. And the goal, indeed, is to recover the model that can still serve as for the intended quality of the inference receiver, but either if it's exposed to noise and transmission, so actually to test the robustness of the communication. Then the second proof of concept, this is more, I would say, system-wise. Actually, it's what we call semantic goal-oriented enable collaborative robots case. We're actually, with end-to-end robot control techniques that use semantic communication to exchange the sensing data to allocate tasks with a goal-oriented approach. And actually, the target is to reduce the communication overhead, and also the amount of data we send, while improving the energy efficiency of the system. And this demo will bring the technology to the TRL number 5. Now, who are the people in the project? So myself from CEA-Leti as the coordinator, then actually the technical manager is Professor Paolo Di Lorenzo for CLIT. Then we have 11 partners from 4 European member states and also 1 Asian affiliate partner in Singapore. We started the project in January this year, and it will run for 3 years. Thank you for your attention. I just want to point you out, we already have one paper describing in details the missions and the project. You can find that already on Internet or archive. And if you have any question offline, you can write to me or to Paolo. In any way, we have a LinkedIn group and a website that will be up actually in a couple of weeks. The domain is already there, but the content will be delivered in a couple of weeks. Thanks very much for your attention.